Greetings from the New Horizon College of Engineering from Department of Civil Engineering. We have privilege to present you the video details related to the lab design and detailing of RCC structural elements. The code is CIV62. So this part of the video lecture will deal with the detailing of slabs. The first thing is one-way slab systems. Slabs are the most common widely used structural elements whose thickness is considerably smaller than their dimensions. They are frequently used as floors, roofs in buildings, decks in bridges, top and bottom of tanks, slabs on grades which is directly support on soils, staircases and so on. Slabs support and transmit loads to the walls or beams supporting them. Sometimes transmit the loads directly to the column by flexure, shear and torsion. In addition to the supporting vertical loads, slabs also act as a deep horizontal girders to resist lateral wind and earthquake loadings. Types of slabs. Depending upon the type of support conditions, slabs may be broadly classified as simply supported, continuous and cantilevered slabs. One such cantilever slab has been shown in the figure for understanding. Slabs may be take various shapes such as rectangle, square, trapezoidal, circular and triangles. While rectangle slabs are frequently used, circular slabs are often found in the tanks. One-way slab systems. The example of one-way slab system is shown here. So you can see this, if one dimension spans more than the other one is something called one-way slab system. That is, one longitudinal span is more than 2 times the transverse direction. It is stated as one-way slab systems. So let us, for example, you can consider this axis. So this slab whose span is more when compared to other directions. So it is a one-way slab, one-way slab, one-way slab. Again, it is a one-way slab. It is a cantilever type of slabs. So in this point, we have to understand that slabs will consist of two directional reinforcements, that is in the longitudinal direction and transverse directions. One reinforcement will be called as a main reinforcement, other will be called as a second reinforcements. The second main reinforcement will be designed for bending, that is for the bending moment that is being calculated depending upon support condition of slabs. And secondary reinforcement will be designed for temperature effects or shrinkage effects, etc. That is for which will be acting as a secondary reinforcements. So based on this figure, you can able to understand that the main reinforcement will be always kept in the shorter span and secondary reinforcement will be kept in the longer span. If you consider this slab, this is the shorter direction, this is the longer span. So main reinforcement will be in this shorter span and secondary reinforcement will be in this longer span. If you consider this slab, this is the direction of my main reinforcements and this is the direction of my secondary reinforcements. Secondary reinforcement will be in the longer span and main reinforcement will be in the shorter span. Again here main reinforcement, shorter span, secondary reinforcement in the longer span. When we compare this slab and this slab, this is a cantilever slab, so which is having no support at the other ends. It has the ability to bend, so this is the direction of main reinforcement and this is the direction of my secondary reinforcement. Shorter span, longer span. Shorter span, main reinforcement. Longer span will be the secondary reinforcements. Behavior of one-way slab systems. One-way slab systems are usually made up of span in shorter span or shorter direction along as the corresponding bending moment. Shear force are the maximums. Direction in which load is carrying, the shorter side is called as a span. The effective span of a design purpose may be obtained by class 22.2 of IS 456. Behavior of slabs in one-way slabs. Direction in which the slab bends is called main direction, as shown in the figure, something we have previously seen. Main reinforcement is placed along the tension of the slabs, usually at the bottom in this direction alone. Steel is provided the transverse direction to take care of temperature and shrinkage effects in that direction. This steel is called distributor steel or secondary reinforcements. It also helps in distribution of loads. This is the direction. This is a typical one which showing the reinforcements in case of masonry and other one is for longer spans. Just imagine this is a slab. it has been supported at two ends. This here I have a unit of masonry support. Here I have a unit of masonry supports. So this is a longer span. This is a shorter span. From this you can understand this. This is the direction of main reinforcement. That is the main shorter span. Longer span will be the second distribution of second reinforcements. The cross section of the same figure has been shown here. That is the clear span and one-way slab system that has been supporting. Next thing, the deflection here. So what happens is when the slab is being loaded, it have a deflection along longer span and the shorter span, but the amount of deflection absorbed by longer span will be higher when compared to shorter span. So if deflection is lower, then the force transmission will be, the shorter span will be higher when compared to longer span. So the main reinforcement should be kept in the shorter span rather than the longer spans. Minimum thickness, the deflection requirement of our slabs, which are the same as those for the beams, which will offer control the depth of my slabs. Most code offers two methods of controlling of deflections. Check the actual deflection against allowable limits. Adopt specific span to depth ratio for which the serviceability can be assumed to be satisfied. The minimum thickness, solid one-way slabs, simply supported, one end continuous, both end continuous and cantilevers. Members not supporting or attached to the particulars of other construction likely to be damaged by large deflections. L by 20, L by 24 on one end continuous and both ends continuous, L by 28, cantilevers L by 10. Same thing if it's of a beams or ribbed slab systems, this kind of classification can be followed. This is as per IS 456 class number 23.2.1. Minimum thickness, deflection is influenced by several parameters, which includes the percentage of age of tension reinforcements and the stress at service loads. In general, the percentage of reinforcement is low, hence we can use a span to the effective ratio that are longer than those used on the beams. So D minimum is equal to span by beam, that is L by D ratio, KT and KC. These are the factors that depends upon temperature and shrinkage effect of my concretes. When one decides to have shallow member, deflection can be kept with the requirement limits by proportionating more tension reinforcement than the required for stronger considerations. Increase the percentage of compression is the best method to control the deflection without increasing the strain in the tension steel beyond the limit as specified by class 37.1 of the code. Minimum thickness should be checked against required fire resistance. This is the spacing. This is something about the spacing of reinforcement in one-way slab systems. Main bar spacing should not be. It should be account of diameter of my bar dB should be less than or equal to d by 8. Center to center spacing should not be greater than 3 times d or 300 mm. So and if you come for distributed bars, the spacing should not be greater than 5 times d or 300 mm, where d stands for effective depth of my section. Next thing, detailing of reinforcement in one-way slab systems. Unless the actual crack width have been checked by direct calculations, the following rules given in the code will ensure the crack width will not generally exceed 0.3 millimeters. Limit on crack width is based on consideration of appearance and durability. The horizontal spacing between the bars, the main reinforcement bar is less than 3 times d or 300 mm. Horizontal spacing between the parallel reinforcement bars, it is nothing but second reinforcement bars of shrinkage and temperature is less than 5 times d or 300 mm. Figure shows the detail of reinforcement in simply supported single span one-way slab systems. Two alternative arrangement of reinforcement are shown: continuous one-way slab systems and in figure A and figure B that comes in the next slide. In the first method, separate straight bars are used for positive moments and negative moments. In second method, top reinforcement bars over the support is provided by bending up alternative bars for positive bending moments. either side of a support with some additional reinforcement bars. So in this case, it is something about the reinforcement here. So if we talk about the here, this is a deal of simply supported beams with uniform distributions. So what happens at the support? I have tension at the top, mid-span tension at the bottom, again the support tension at the top. So how what the code says as per SP34, 50% of AST can be provided the supports. So 0.5 times AST. So half of the bar can be cranked to carry to the top in 1 meter square area. So you can see this alternative bars can be cranked top as well as bottom. This crank length can be 0.1 times Lx, where Lx is something but the effective length of my slab systems. S is nothing but spacing of my reinforcements. So you can see this the 2 represents is a secondary reinforcement bars which is in the longer span. 1 represents the main reinforcement bar which is spanning the shorter spans. At the supports, minimum 2 numbers of distributed reinforcement bars to be provided. The cross section of section BB is being shown here. So main reinforcement, secondary reinforcement arrangements are being shown here for understanding. This is the detail of continuous slab systems. So from the supports 0.3 times L, additional reinforcement should be provided. The area of steel should be greater than 0.5 times AST, and the top reinforcement for tension at the top should be more than 0.15 times CL1. Same way opposite side can be provided, and at the bottom reinforcement again the same 0.15 times L1 can be provided. If it is of a curtailments, small difference is there. Instead of yes, mostly both things, those things will be matching. That is, if I go instead of going for crank bars, if I go for curtailment bars, that is by using a straight bars, I can using this concept, that is spacing this from the clear face of my column can be adopted for providing area of steel for those arrangements. So next thing is about two-way slab systems. When the aspect ratio of a floor panel is less than 2, then the contribution of longer span in carrying a floor load becomes substantial since the floor load is transmitted in 2 directions. This type of slab is something called two-way slab systems. Flexural reinforcement has to be designed in both directions. So in general, in simple, if L by D ratio is less than 2, it will be acting as a two-way slab systems. So the load will be mutually shared by 2 axes. So two-way slab systems includes two-way slabs, solid slabs supported by beams, flat slabs, flat plates, and waffle slabs, etc. And solid slabs on the beam on the four sides is generally referred to as two-way slab systems. So this is an different in behavior of one-way slab system and two-way slab systems. In one-way slab systems, slab force will be transmitted in only one axis, that is either in x-axis or y-axis. In two-way systems, in both the axes, the forces will be transferred. It means that all 4 sides of my slabs will be taking care of loads to the supporting system. It may be beams or slabs, beams or columns. Minimum thickness of slabs. Slabs is the primary factor affecting the serviceability and strength, shear strength. Fire resistance requirement may also should be governed while deciding cover and slab thickness. Vertical deflection limit may be assumed to be satisfied in two-way slab systems with the shorter span up to 3.5 meter with mild steel reinforcement, and for load class up to 3 kg per meter square when slab to over depth ratios are not greater than the following class values. As per class number 24.1 and 23.2 of IS 456, for simply supported slabs is 35, continuous slab it is 40. For Fe415 grade steels, this value can be multiplied by in terms of 0.8 because the steel will be getting higher brittle in nature. So I have to increase the cross section of my steel, cross section of my slab systems. So this shows the detailed arrangement of my two-way slab systems with bend-up bars. So same concept. Alternative bars should be cranked so that 0.5% of AST can be provided. The area of steel and the span of area of steel will be 0.1 times L1 or L2. That is from the face of my column 0.1 times L1. The tension reinforcement can be cranked down for the support to the midspan so that the reinforcement can able to take the tension at the support as well as the midspans. In this case, both the directions spanning of reinforcement will be of a main reinforcements. So since L by D ratio is less than 2, both the axes, the reinforcement what we are touching should be often main reinforcement for arrangements. Detail of torsional reinforcement at the corners. Torsional reinforcement and torsional moments are developed near the corners of my simply supported slabs, which will result in uplift of my corners as shown in the figure unless the slab has been restrained at the corners. This will result in cracking of slabs near the corners as shown in the figure. Hence, torsional reinforcement are to be provided in the corners of my slab to take care of these torsional moments. Two type of reinforcements indicate figures C and D here. You can look at here at point A, something like a simply supported slab. When it is being loaded, our corners uplift will be there. This corner uplift may result in bottom cracking and top cracking, something like this. This kind of cracking may occur at this all four corners. For this kind of edge type of reinforcement can be provided. This is something called torsional reinforcement that will be resisting the amount of force. This amount of, that is the area of steel, or what is the span up to which the area is to be provided is LE by 5 on both sides, where LE stands for effective length of my slabs or effective longer clear span of my slabs. Again here, this is a mat-like of pattern in case of square or rectangular arranged square shapes. Here the separate trapezoidal type of arrangements can be provided. That is at the corner, the reinforcement can be provided something like this. Detail of restrictions of two-way slabs. When restriction slabs are designed by using moment coefficients as given in table 26 of IS 456, they should be detailed as shown below. Tension steel calculator for positive design moments at the short and longer span should be provided as shown on the figure. At the bottom of the mid span in the mild steel in the shorter and longer span directly respectively. Tension steel calculator for negative design moments in the shorter span and longer spans of the continuous support should be provided at the top and uniform distributed across the edge strip of a short and long spans respectively shown here. As shown in the figure will be proceeding. As the discontinuous edge, negative bending moments may rise due to partial fixity. Hence, to safeguard against such situations, 50% of a bottom steel at the midspan should be provided at these edges, and such a steel should not exceed the length of 0.1 times Lx or 0.1 times Ly for the face of the supports. Reinforcement in the edge strip parallel to the edge need not exceed the minimum area of tension reinforcement together with the reinforcement of torsion as per class D 1.7 of the course. So this figure will talk about the reinforcement detail of my slabs. So you can see this area of steel. So the bottom reinforcement, it is a continuous slab systems. Bottom should be 0.25 times Ly and extra reinforcement top will be 0.15 times Ly. Same case at the opposite sides. So this area of steel has to be provided something like this as if shown in the case of continuous slab systems. So this will be divided as middle strip, edge strips. So this following conditions should be followed when we are providing reinforcement for this kind of continuous slab systems. So this is again the reinforcement detail for the continuous simple rules for curtailment of bars in continuous slab systems. The AST 0.5 times AST the two supports from the center 0.15 times L1 on the interior span from the center 0.25 times L1. Again opposite side 0.25 times L1. Bottom reinforcement 0.3 times L1. At the support here the distance should be from the 0.15 times L1 here. This is the arrangement of reinforcement detail that can be provided for arrangements. Detail of torsional reinforcement at the corners. Torsional reinforcement should be provided at the corners where the slab is simply supported on both the ends meeting at the corners. Following points should be noted. This torsional reinforcement should be provided at the top and bottom in meshes or grid patterns, each layers of bar space parallel to side of a slabs extending from edge to the minimum distance of 1/5 of a shorter span. That is L by 5 times the span should be the provision of torsional reinforcements. Torsional reinforcements equal to half that described in the one should be provided at corner where one edge of a slab is continuous, other edge is discontinuous. Torsional reinforcement need not to be provided when both edges meet at corners or discontinuous. Two-way slabs can be pre-chamfered to counteract the effect of long-term deflection due to care is needed in applying such chamfers. It is desirable to limit the chamfering to maximum half of total deflections. This is something about the reinforcement detail for the torsional reinforcements. So that can be provided for the distance of 0.5 times, 0.2 times L at the both. This part of AutoCAD file will help you to understand how we can plot or how we can draft the two-way slab reinforcement detailing. Please listen to the comments that has been displayed and the drawing procedures. Thanks for joining us.